Hi, everybody. This is 4.1 um, inverse functions. We're going to be looking at something called inverse functions. And when we write a function, it looks like this, and then whatever the function is. So this is a function. An inverse function looks a little different. It has a -1 power on the f. So we call this an inverse function. So we call that an inverse function. And we'll talk more about inverse functions and how we recognize them and how we create them and all that here in a little bit. But I just want you to know the symbology. When we see this, when we see this, we know it's a function, and we see a -1 power on that function, we know it's the inverse of the function f. All right, so determine whether or not the function is 1-to-1. First of all, let's determine, remember how to determine if a function, if a graph is a function. Anybody remember how to look at this graph and say, oh, that's a function? How do we remember how we did that? For a function, we did something called the vertical line test. If we drew a vertical line and it crossed only one time, if I could draw a good vertical line, then it was a function. Vertical line test, graph cross the line, vertical line test. The line crosses only one point on the graph. When you draw a vertical line, and if it and you just draw as many as you want, if it can only cross one point on the graph, then it is a function, yes. Now, to determine if something is 1-to-1, if a function is 1-to-1, and we'll figure out what 1-to-1 here means in a little bit, we're going to do something called the horizontal line test. If you draw a line and it crosses only one time, oh, it only crossed one time. However, you have to try to cross more than once. Look at this. It crosses more than once. So this is not 1-to-1. Horizontal line test, graph crosses the line, the horizontal line crosses at only one place. So here it crosses at more than one place. Here it crosses at one, but you have to try to keep on drawing horizontal. Oh, there's another one that crosses at more than one place. This graph is not 1-to-1. Not 1-to-1. All right, so let's move on. Here's a graph. If I draw a horizontal line, it only crosses one place. If I can draw a good horizontal line. It's hard to see, but this graph is going down and down. If you drew a really good graph, sorry, it only crosses at one place. So yes, since it's a horizontal line, crosses graph only one place. This graph is 1 to 1. All righty. Now, what if we don't have a graph like number 3? We have to remember what the graph looks like. And if you remember X3 graphs look like this. Without any other X's, an X3 graph looks like that. +6 means the graph goes up, and the 5 in front means the graph gets skinnier. Right? It's in the correct terminology is it stretches. So this is an X3 graph that goes up 6 spots. So it kind of looks like this. If I could draw it a little better, there we go. I don't know. It's not easy for me to draw this thing. Something. It looks kind of like that, right? I'm still really bad at it. Let's try it one more time. Okay, there we go. So if I do a horizontal line test on this, no matter where I draw this horizontal line, it crosses the graph only one spot. So yes, this graph is 1 to 1. By the way, if a graph is 1 to 1, then it has an inverse. So let me write that down. If a graph is 1 to 1, then it has an inverse. In other words, if this function is 1 to 1, then we know it has an inverse graph. An inverse function, an inverse graph. Okay, so we know that. So number 3, yes, that is 1 to 1 because we did the horizontal line test. Number 4, let's take a look at what number 4 looks like. It's an x squared graph. That's a parabola because there's a positive number in front. You know, there's nothing in front. There's no negative. Negative means it's upside down parabola. A -9 on the inside moves the graph to the right. So this normally the graph is right here, but we're going to move it to the right 9 spots. A negative on the inside moves the graph to the right. And our graph should look something like that. Does this pass the horizontal line test? No. No, it is not 1 to 1. It fails horizontal line test. In other words, it crosses the graph in more than one spot. So it fails the horizontal line test. Everybody okay so far?
Yes.
Yes, sir.
Glad you guys are alive and awake. Okay. Number 5. I like to write this. Let me write. Here's function f. If we want to know if these two functions are inverse, here's function g. And I want to write it with as a t table. F, if you look, here's the first coordinate, -2, -4. 1, 4 is the next coordinate, 4, -2, and 8, 11. G, the function g has the following coordinates, -4, -2, 4, 1, -2, 4, and 11, 8. The question is, are these two inverses? Are they inverses to one another? Inverse functions have the same x and y coordinates if you switch one of them. In other words, if I change g, let's watch what I do with g, x and y. I'm erasing the x and y, and I'm changing it to y and x. Are the y coordinates here? Oh, but maybe I shouldn't have changed it to x and y. Let's keep it. We're going to keep it the same. That's. I mean, it's correct what I did, but we're going to keep it the same. If the y coordinates of one function equal the x coordinates of the next function, and then vice versa, the x coordinates of one function equals the y of the other function, then they're inverses. Look here, y, we have -4. There's a -4 for x. We have 4 and 4, -2 and -2, 11 and 11. So the y of one function equals the x of the other. Now try it the other way around. I'm going to switch colors. The x of one function should equal the y of the other. -2 and -2, 1 and 1, 4 and 4, and 8 and 8. So decide whether the given functions are inverses. Yes, they are inverses because all x of one function equal the y of the other. And you have to look at both. All y of one function equal the x of the other. Just like we did. Check all the x of one function. Does it equal the y of the other? Yes. Check the y of one function. Does it equal the x of the other? Yes. So yes, it is an inverse. All righty. I'm going to do another one. Let's say I have x, y, 1, 2, 3, -1, 2, 5. And in my other function, I have -1, 2, 5, and I have -1, 2, 3. And the question is, are these functions inverse? Do all the x equal all the y? And here's a 3, here's a 2. This one's a 1, and this one's a -1. And you can stop right there. No, these two are not inverses. Because all the x of one function has to equal all the y of the other. And all the y, here, all the y do equal the x. That's okay. But there is one piece that didn't work. So the whole thing is not an inverse. These two functions are not inverses of one another. These two functions are not inverses of one another. Okay? All right, number 6. How many graphs do we have? State whether the pair of functions are inverses. So now we have graphs. Well, one way of doing this, here's one, I'm going to show you two ways of doing this problem. I'm going to call this graph F. I'm going to call this graph F, and I'm going to call, they have this line here, and I'm going to talk about this line in a second. And here's a graph G. So I want to write some coordinates for F and G. I'm going to write some coordinates for F and G. So let's start off. Can somebody tell me what x0 equals? What's the y when x0? Let's see if anybody's actually paying attention and can answer this question. For a function f, when x is 0, what does the y equal? Anybody know?
3.
Louder? I think he said 3. Do you see this coordinate right here? That coordinate is x0, y3. Thank you. Let's go to G function. Do you see, if the y is 3, we can make the x 3 over here. If the x is 3 in the G function, that means this is the point right here, the x is 3. What does the y equal in this coordinate? It kind of looks like it's 2. Do you see how you can do one coordinate? The y and the x are the same, but the x and the y are not the same. So these are not inverses. These are not inverses. And I mean, that's just one point. You can try it with a different point. Let me create another point. Oh, let's get back there. And I erased everything there. Let's try it with a different point. X and Y for F, and then X and Y for G. Let's say X is 1 for F. If I go up to 1 for F, it's about right here. It looks like Y is 5. So go to Y. You see, if y is 5 in one function, make x 5 in the other function. I just put a 5 over here because it should be opposite. And then find out what the y equals. When y is, here's function g, that was function f. Function g, when x is 5, it looks like y is 2.5. This coordinate, x is 5, but y is 2.5. And they don't match. This x does not match this. These two match. That's fine, the y and the x. but these two don't. So this is not an inverse. These two functions are not inverses from each other. They're not inverses. And there's another way of looking at this. There's another way, and I'm going to show you that here in a second. But this is just one quick way of doing it. I mean, you got to be good with coordinates. You got to remember all that stuff we've learned in the past. I want to show you what this dotted line is. This dotted line is a function itself, and this dotted line is called y equals x. It's an invisible line on the graph. So we dot it because they want to create this invisible line on the graph. The invisible line is y equals x. I'm going to show you. Here's a function y equals x. If x is 1, then y is 1. You see, the function is called y equals x. They have to equal each other. If x is 0, y is 0. If x is 2, y is 2. If x is negative 1, y is negative 1. So let me graph these. 0, 0, 1, 1, 2, 2, negative 1, negative 1. Do you see how they all line up on this dotted line, y equals x? They all line up on that dotted line. So this line, this dotted line, it's invisible. It's called the y equals x line. For something to be inverses, if two functions are inverses, they should mirror each other on the y equals x line. In other words, look at this. Here's a function, this blue one. Here's a function. If I do a mirror of this red function, you see, if I fold it over on the y equals x line, it folds over to right here. It doesn't fold over to the blue line. So this is not an inverse. This is not in, these two functions are not inverses. And I'm going to show you what I mean by mirror image in a second. Well, so we're going to find one that's an inverse. Let me show you. If I drew a graph, here is my y equals x line. I mean, well, you don't, let's draw the y equals x line. I'm going to draw it in purple. This is my y equals x line. Okay, so here's one function. Let's say this is the function. And then I want to do another function in blue. Do you see if on this y equals x line, if I fold this over to the other side, it lines up. If I fold this over to the other side, it lines up. The two graphs lined up. If you fold this paper over, this black graph will line up on the blue graph. This black graph will line up on the blue graph. When you fold it over on this line here, they mirror each other. They mirror on the y equals x line. So yes, these two functions that I just wrote are inverses. These two functions are inverses because they fold over on the y equals x line. And that y equals x line is not always going to be drawn for you. You have to create it sometimes to look at it. All righty. For this function, For the function as defined that is one-to-one, graph f and graph its inverse. So first, we want to graph f. By the way, our function f is just 2x. There it is right here. So we want to graph it. The way to graph it is make some points. And somebody tell me a point that I should use for x. What's the first x point I should use? Anybody?
1.
No! I thought we learned already. You can use 1, by the way. The first one I would always do is plug in 0. If I plug in, here's our function again. 2 times x. If I plug 0 into there, oops, I got rid of it. Damn it, I did that again. I pushed the wrong button. The function x equals 2x, and we have this, x and y. If I put 0 into x, 2 times 0 is 0. That's always the easiest, to put a 0 into something. Then I'm going to use his recommendation of 1. If I put 1 into x, 2 times 1, my function equals this. Remember, don't forget, this is the same thing as y. Then my y equals 2. I'm going to put another number in there, 2. If I put 2 into x, 2 times 2, I get y equals 4. Okay, I'm going to graph these points. 0, 0, 1, 2, and 2, 4. If I draw the line and extend it, that's what the function looks like. This is function f. I now have to draw its inverse, and I'm going to draw its inverse in, if it lets me, blue. Remember, we annotate an inverse by putting a -1 power for the f. Can somebody tell me what the coordinates I should use for my inverse? Anybody? What coordinates
0.
should I use? Say that again.
0.
Well, you can start, yes, you can, but I mean, remember, if I have a function and its inverse, the x's are now the y's, 0, 1, and 2. The y's over here are now the x's, 0, 2, 4. So remember, one function and its inverse, the x's become the y's in the inverse function, and the y's in the regular function become the x's in the inverse function. So the x's, once again, become the y's over here, and the y's become the x's. So let's graph this graph in blue. 0, 0, 2, 1, and 4, 2. If I connect these dots, I get something that looks like this. Now there's one more thing I need to do. Let me draw my y equals x line, right? At 0, 0, 1, 1, 2, 2, 3, 3, where y equals x. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, -2. Do you see? Here's the graph. There, let me draw it as a dotted line. And do you see, if I drew this correctly, a little messy, but this, for the function defined one-to-one graph, for the function as defined, one-to-one graph, graph f and -f, all right? So the black one was f, And the inverse function is the blue one. You can either way. But do you see their inverses? They mirror image the xy. If I drew it correctly, they mirror image the xy. So you can graph them by just putting three or four coordinates for the function, and switching the x's with the y's for the inverse and the y's with the x's, and then you'll be able to graph its inverse. So all you have to really do is do one function t-table, and then you have two different functions, one function and its inverse, and you can graph both of them. And if you look at it compared to the y equals x, they will mirror image each other.
Mr. Shotman,
Yes.
does the y equal x have to cross in the middle of where the f of x and the inverse crossed for
No.
it to always mirror?
No. In
Okay.
fact, let me just show you. You could actually have an inverse that looks like this. When you say middle, no, you can have an inverse that looks like this. It has to cross at some point. Well, not necessarily cross at some point. And then if I have the other graph, it could, right here, and these mirror image each other. It doesn't have to cross here. And by the way, it doesn't have to cross each other. I can do something like this. It's normally when we have lines, they will cross each other. But I can do a graph that looks like this. And then have another graph on the other side that looks, you see, as the mirror image, and they're inverses of each other, because if you flip them over, they look at each other. So it doesn't have to cross. When we have straight lines, linear equations, linear functions, they do cross at a point. But they don't have to. There's always a graph that shows us that. Oh, and here's an example. Actually, I think we're going to have an example. Let me see if we have an example down here. I'm going to check. If not, I'll create my own example. Yes, this one right here. So let's do this one right here. This is an example where they won't cross. Let me draw the y equals x line first to show you. 0, 0, 1, 1, 2, 2. This is the y equals x line. Now, first, I want to graph the square root First, I want to graph this function. And I'm going to put some x and y's in there. By the way, this is a square root graph, correct? It looks like this. I mean, if I drew it on my graph, it would look something like this. But the +5 moves it to the left 5 spots. So I'm going to erase it and move this graph to the left 5 spots. This is what the graph would look like. So this is what this graph looks like. And I'm going to show you some test points. If I put -5, oh wait, this is 5, not 4. If I put -5 into this function, here's my function, square root of x plus 5. If I put negative, I did it again. I keep on pushing the wrong button. This is my function graph. If I put -5 in here, if x is negative 5. Then negative 5 plus 5 is 0. The square root of 0 does equal 0. By the way, I want to show you also, don't forget, if I put negative 6 in here, negative 6 plus 5 is negative 1, and you can't take the square root of negative 1. It's an error. Do you see? So, I mean, I can't use negative 6 because that gives me an error. So now I'm going to try something else that I can find. And I'm trying to get perfect squares. I'm going to use a negative 1. I'm going to use, so this didn't work. I'm going to put a negative 1 in there. Do you see? Negative 1 plus 5 is 4. And we know what the square root of 4 is. The square root of 4 is 2. I'm also going to use another number. Let's see what else I can put in here. I'm trying to pick numbers that are easy square roots. If I make this 1, the square root of 1 is 1. So if I put a negative 4 in here, negative 4 plus 5 is 1, and the square root of 1, so if I put a negative 4 in there, I get square root of 1, and square root of 1 equals 1. And I'm going to put one more in here. I want a good positive number that I can add. Anybody know a positive number I can put in here that will, I mean, any number will work, by the way. Any positive number will work. But what's a good positive number that will give me a perfect square? How about 4? 4 plus 5 is 9. The square root of 9, so I'm putting 4 in there, and the square root of 9 is 3. You see, you could have put 5 in there, by the way, as square root of 10, and then on your calculator, the square root of 10. Is 4 point something. It's a decimal, but I wanted whole numbers. So I'm going to graph this function here, negative 5, 0, negative 5, 0. And then I'm going to use this point, negative 4, 1. Then this point, negative 1, 2. And then this point, 4 and 3. So there's my square root function. Okay. Now, don't forget, I know for them to be inverses, they have to go through 1, 1, 2, 2, 3, 3, 4, 4. They have to go through this y equals x. This is the mirror image, if I drew it correctly. This is the mirror image y equals x. Do you see the mirror image of this at negative 5 would be over here at negative 5? If I mirrored it, it would be at negative 5. I just want to make sure we know that. We can see that. So here are my inverse. I'm going to change my color to blue. Here's my inverse function, x and y. I'm going to try to just switch these. Negative 5, 0. Let's do 0, negative 5. Negative 1, 2. Remember, we just switched them and we put 2, negative 1. Negative 4, 1 is 1, negative 4. And 4, 3 is 3, 4. Let's graph these and I'll show you. I don't think we'll have the whole graph. 0, negative 5 is right. Oh, maybe we do. 0, negative 5 is right here. 2, negative 1 is right here. 1, negative 4 is right here. Hey, it looks like it's working. And 3, 4 is right here. Do you see this blue graph? It looks like it's going like this. If I could draw it a little bit better. There we go. There's what the blue graph looks like. And if you notice, they're mirror images of each other across the y equals x, across the dotted line. So that worked out really well by switching those that we picked. You had for a square root graph, I just had to pick more points so I could see the shape better. I know square root graph is going to look like this of a regular function. Now the inverse is not going to look like that. The inverse is going to be a mirror image of the y equals x line. So it should look like we just drew, the black and the blue graph. Those are the inverses of each other. And yes, those two do cross each other at some point. I'm going to, even though everyone we have crosses each other at some point, they don't always do that. They don't always. It just happens. We're getting the ones that do, which is good. Okay, we're going to try this graph. Oh, Lordy. How many more do we have? I think this might be the last one, right? Yes, this is the last one. Good. Here's my function. Let's do it, the first one in black. The function is x3 plus 5, and we're going to do a graph of our function. I'm going to plug numbers in there. Let's start with 0 for x. If I put a 0 in here, 0 to the third power plus 5 is 5. Then I'm going to put a 1 in there. One to the third power is 1. 1 plus 5 is 6. I'll put a 2 in there. 2 to the third power is 8. 8 plus 5 is 13. We're off the chart already. Our chart only goes 10, 10, 10. I'm going to try a negative number. Negative 1 to the third power is negative 1 times negative 1 times is negative 1. Negative 1 plus 5 is 4. You can try this out on your calculator. Negative 2 to the third power is negative 8. Negative 8 plus 5 is a negative 3. So let's try to graph these and see what we got. We got 0, 5. Right, don't forget, an x3 graph looks like this. A little bit better than this. There we go. Something like that. There we go. So 0, 5, but a plus 5 is up 5. 1, 6, 2, 13. Here's 2. 13 would be way up here. So the graph goes up like that. Then I have negative 1, 4, and negative 2, negative 3. You see, and then it curves down. That's what an x3 graph looks like. This is our function. Next, we're going to do our inverse function. And before I do the inverse function, I want to do that y equals x function. All right, so what happened? I'm telling you, my computer's playing tricks on me. I must have hit something. Let me see. Share screen. Oh, that's. I need to get rid of that. I need to change that. I must have clicked on something on that screen. Oh, this is not the graph I want. Okay, so back to this one. I'm going to write this things back down. Why is my thing so sensitive today? Let me draw this right here. That one and that one. That's my y equals x. Of course, the last one would have to give me problems. And we had the x and y of the function, and I put 0 in there, got 5. I put 1 in there, got 6. I put 2 in there, got 13. Oh, that's why it's not acting up. I put -1 in there, got 4. I put -2 in there, and I got -3. And I got 0, 5, 1, 1. No, 1, 6. This should be 1, 6. And 2, 13. And then I got -1, 4, and -2, -3. So there's function f. Now we're going to do function f inverse. And we're just going to switch the x's and y's. So the x's were 0, 1, 2, -1, -2. So I'm going to make those the y's. 0, 1, 2, -1, and -2. The y's were 5, 6, 13, 4, and -3. So let me graph these. 5, 0, 6, 1. 13, 2 would be about right here, right? This is 13, 2. 4, -1, and -3, -2 would be right here. So this is what the graph would look like. And sure enough, look, they do mirror image on, they do mirror each other. You know, you can fold them over on the y equals x line. If you look at that, they do mirror image each other. So there's our function in black, and our inverse function is in blue. And that's all I had for the day. Did I share my? Am I sharing my screen right now?
Yes, we can see it.
Okay, well, I can't what happened? Where? Oh, there it is. Okay. Stop recording.